Jesse Christiansen from Nexi, Caltech, telling us about my favorite subject, Know Thy Star.
I took it out.
You took out Know Thy Star? What's your new title?
Just without Know Thy Star.
Just without Know Thy Star. How Gaia grounds.
It didn't fit on the slide, Dan. Give me a break.
I have the same problem. Anyway, so Jesse will tell us about how Gaia grounds Kepler K2, TESS, and direct imaging.
Thanks, Dan. Does this need to be plugged in now, Ellen, or can I use it?
No, you can use it.
Okay.
Your turn.
Thank you. Hi, everyone. So yes, I slightly modified the title and I'm about to slightly modify it even further. I looked at the schedule and all of Thursday is about Gaia and direct imaging. So I'm really just not going to talk about that because I can't imagine anything I would say that the amazing folks who are going to talk on Thursday aren't also going to say. So I'm going to stick with my specialty, which is Kepler K2 and Test. So we've talked a lot so far about how Gaia helps us understand planet parameters better. I'm going to take this talk as an opportunity to explain why that's cool. Why is that important? What do we learn if we know something better? Why is it better to know something at 5% instead of 10%? What are the new interesting physical insights that we've gleaned about planets and planet populations because of Gaia? Okay. So first I'll start by talking about the planets that we found so far. We heard a little bit of that just now, but we'll go through it a bit. Then I'm going to go through some examples of ways that our improved stellar parameters and understanding of the galaxy have helped us understand planets better. And finally, a little bit about how Gaia will help us in the future to keep doing this, keep tackling these questions. Okay, so let's start with planets. Okay, so this is a plot showing as a function of time how many planets we found. And I'm about to, at the very end of the talk, explain why we change the left-hand side of this plot. But in the meantime, most of the planets we've found so far have been via the transit method, which you've heard about a few times now. Something like 3/4 of the planets that we've found so far have been found with transit. Radial velocity has contributed about 1,000, and you've heard about that, and we'll talk about a bit more about that as well. Microlensing, which we're not going to talk about, has found about 130. That's a different Sagan workshop. Go look that up on YouTube. That was great, but we're not going to talk about it here. And imaging, again, not really going to talk about it because there's going to be a bunch on that on Thursday. And then, so far we found just over 5,000 planets. And you heard from Michael's talk yesterday that the expected yield from Gaia is 20,000. So quadrupling, quintupling the number of known planets just out of one mission. So for me, as a scientist at Archive, that's pretty exciting in terms of job security. For me, as a scientist, that's pretty exciting because there's a lot more planets to analyze and do a lot of interesting population work with. Okay, so let's talk about what we found so far. On this plot, I'm showing on the x-axis is the semi-major axis, the distance from the start of the planet. And on the y-axis, I'm showing the planet mass or minimum mass from radial velocity. We'll come back to that in a minute on the y-axis. So this purple population here is the transiting planets that have been found. That's those 3/4 of planets that have been found by transit. There's a transit. I'm not going to go back into how Gaia helps us get better parameters in detail because Dan and Roxanne have talked about those. But I will say this is where I get to use the giant cursor. Guys, the cursor is real huge. Look at it. All right. So the observables from the transit light curves are the orbital period, the transit depth, and the transit duration. It's comically large. Gaia helps us with things like the stellar temperature and the stellar radius, which when combined with those observables give us better understanding of the planet size, stellar density, and the stellar temperature. Just recapping what you've already heard, because that's good pedagogy, I'm told. Okay. Kepler K2 and Test is what I'm going to talk about now. These are the missions that have contributed a large fraction of these transiting planets. Kepler was a 1-meter telescope that was launched in 2009. It stared one patch of sky for 4 years and found about 2,300 confirmed planets. Now I've switched it up slightly on the x-axis. Now it's period, not semi-major axis, just to keep you on your toes. So period on the x-axis, planet radius on the y-axis. So Earth would be out here somewhere, one Earth radius, 365 days. And what you can see is that Kepler did not find any Earth-like planets, which is a major bummer because that's what it was designed to do. But it did find lots of other planets, which are all really interesting, and we'll find out more about them. K2 was the sequel to Kepler. It took over in 2013 and went to 2018 after the second reaction wheel failed on Kepler. It actually stared at a set of fields around the ecliptic plane. So where Kepler did that one field out of the plane, this is like Todd's exoplanet dance, but it's a telescope mission dance. So Kepler was out of the plane, and then K2 was in the ecliptic plane. It did a survey around the plane. And so it was actually not observing any given field for as long as Kepler observed. So it's sensitive to shorter period planets. So you can see it doesn't go to as long a period. And then TESS is our most recent NASA planet finder. K2 ended up running out of fuel in 2018, just coincidentally, but in terms of the narrative of planet hunting, so nice. 2018 was also when TESS launched. So literally they could just pass the baton from the Kepler telescope to the TESS telescope. So TESS is doing an all sky, now I'll add to the dance, an all sky survey. So the whole Northern Hemisphere and the whole Southern Hemisphere. And only staring at most of the sky for 27 days at a time. So generally sensitive to even more short period planets, except right at the top and right at the bottom. The dance just writes itself. Right at the top and right at the bottom where the fields overlap and you get a longer set of observations. So you get some longer period planets out here. So put those all together. This is the transiting population from Kepler K2 and Test. And my job is to explain how Gaia helped us post facto understand these planets better. All right, so those are the transiting planets. Radial velocity, I'm not going to go into too much detail, but to recap, the observables from the radial velocity are the orbital period and the eccentricity and the amplitude of the radial velocity signal. Gaia helps us improve our stellar temperatures, our stellar masses, and the inclinations of the orbits if we have an orbit with Gaia, which helps us, again, improve the temperature of the planet. And if we have the orbit, gives us the actual mass instead of a minimum mass that we get from radial velocity. And this will be important and depressing later in the talk. Spoilers. Okay, microlensing. We're just not going to talk about it. Those are the microlensing planets. Direct imaging. No, I was serious. We're not going to talk about microlensing. These are the direct imaging planets, which you will hear more about on Thursday. And I do not want to preempt anyone's very, very cool results. Okay, so put them all together. And these are something about some large fraction of the 5,000 planets that we found. Excitingly, over the history of exploration of exoplanets, we've now covered like 6 orders of magnitude in separation from the star and like 5 orders of magnitude in mass. We really have found an incredible diversity of exoplanets in an incredible variety of environments. So it's really, you know, a testament to the field, how far we've come in just 30 years from nothing to 5,000. Now, just to highlight in context, what Michael was talking about yesterday with the 20,000-ish Gaia planets, this is kind of the area where Gaia astrometry will be sensitive. So large-ish planets in separations out to about 5 or 6 or 7 AU. So cold giant planets, Jupiter-like planets. And if we have time at the end, we'll talk about why that's cool. Okay, so those are the planets we found so far, largely from Kepler K2 and TESS. The best ones, of course. Okay. So why does it help us to have better stellar parameters? I mean, it's nice to have better numbers, but honestly, at some point, why is 0.5% better than 1%? It's better when it tells us something new about the physical mechanisms that build and sculpt and migrate and evolve planets, right? We want to get to the underlying physics. What's happening? How do these planets form? Why are they where we see them today? And these kinds of things can emerge when you have a really well-characterized population of planets. So let's have an example pre-Gaia, and then we'll bring Gaia in. Okay. The point of Kepler was statistics. It was a statistics mission. How common are Earth-sized planets in the habitable zones of sun-like stars? While we're on the way there, which is a very difficult journey, let's work out how common other kinds of planets are, closer in, bigger planets, easier to do. Okay, so this is a plot from Andrew Howard's paper from 2012 using the Kepler data, showing as a function of planet radius on the x-axis, so this is planet radius in Earth radii, so Earth is down here at 1, showing the number of planets per star around solar-like stars with short periods, less than 50 days. And what you can see is that giant planets are less common than medium-sized planets. And then when they got down to about 2 Earth radii, about half the size of Neptune, they started to not have good constraints on the radio. But it looked like if you just kept that trend going, that you would have more and more small planets per star if that trend kept going. So the California Kepler survey went and got better stellar parameters for something like 1,000 stars that had Kepler candidates around them. And what they showed with these better stellar parameters, which gave you better planet parameters, was that that's actually not what happened. The trend did not continue. And in fact, it was much more complicated between 1 and 4 Earth radii than what we thought, which is that it was bimodal. So there are 2 populations of small planets, a super Earth size population between 1 and 1.8, this one here, and a sub-Neptune size population between about 1.8 and 3. So 4 Earth radii is the size of Neptune. Okay, so this is the radius valley. You've seen it already, but it emerged because we got better stellar parameters. Now, there had been some predictions that something like this planet radius valley might exist to do with different ways that planets form, which we'll get back to. So it wasn't wholly unprecedented, but I think a lot of observers who weren't maybe paying as much attention to planet formation theories as they could have were taken by surprise. Okay, so how did Gaia help us? So when Gaia DR2 came out, a lot of work was done to reanalyze the Kepler stars. So remember, the California Kepler survey just did 1,000 stars that had candidates. But now we had Gaia DR2 for the whole Kepler field, which is 200,000 stars. So people went back and reanalyzed Kepler stellar parameters using Gaia DR2, using the better distances, using the better colors and radii and masses to get better planet parameters. So what I'm showing here on the left is how much better the stellar radius uncertainty got between before Gaia DR2 and DR2. So before, the median percentage fractional stellar radius uncertainty was 11%. So most stars had an uncertainty of about 11%. After Gaia, the median stellar radius uncertainty was 3%. So we'd really been able to bring that down. And same when you propagate that through using the equations that Dan showed yesterday, that translates to a reduction in the error on the planet radius from 13% to 5%. So we knew the planet radii much better. And what that meant was actually we could tease out new correlations. So what this is the same planet radius valley I showed you before. It's turned sideways now. So here's this big lump here is the super Earths, and this big lump here is the sub-Neptunes. But what you can see is the location of the valley, where the minimum is between the super Earths and sub-Neptunes, changes as a function of the stellar mass. Right? For lower mass stars, the minimum is at lower mass planets. And for higher mass stars, the minimum changes to higher mass planets. And this was because we had better stellar parameters and we could actually tease this out. Now, this is for that 1,000 California Kepler survey planets. Travis Berger came and did it for the whole Kepler catalog. And you can see that this holds. This is the same thing, stellar mass on the x-axis, the location of that minimum on the y-axis. And you can see that it is a function of mass. Why is this interesting? Okay, cool. It's a correlation. What does it tell us? So I said that we predicted that there would be a planet radius valley. Not me. I'm not that clever. Some theorists predicted that there would be a planet radius valley. Why? There are 2 predominant theories as to why there might be a planet radius valley. One is photoevaporation, is that the planets start with atmospheres, but they're really close to their stars. These are still pretty short period. This is less than 50 days. And that this radiation from the star blows away your atmosphere if you're too small. If you don't have enough gravitational energy to hold onto your atmosphere, it gets blown away. So you end up as a smaller sized planet. And there's some mass at which you're big enough to hold onto your atmosphere, so you keep it. So you end up with this bimodal distribution. Something that's too small loses its atmosphere. Something that's a bit bigger stays big. Are you guys waving at me? Okay. Everybody breathe. Okay, photoevaporation. Better? Okay, thank you. Sorry, everybody, I'll just start again. No, it's fine. It's being recorded. Watch it later if you didn't hear that. Photoevaporation is one idea, that the radiation from the star is stripping off your atmosphere if you're too small, and you end up with a bimodal distribution. Another theory is called core-powered mass loss, core-powered inside the planet. As planets are forming, they have a lot of residual heat. The outer solar system planets in our solar system still have residual heat from formation that they're radiating away. And that radiation, if it's strong enough, can push an atmosphere off, right? Same kind of idea, but instead of the radiation being external coming from the star, it's coming from the inside of the newly forming planet. So much heat is coming out that it's driving away the atmosphere. So these two theories actually predict that there'll be a bimodal distribution. They also predict that this will be different depending on the star's mass, and different depending on the star's age. So you can use this much finer grained information to differentiate between these two theories, which make very similar predictions about where the valley is, but different predictions about where the valley is as a function of mass and as a function of age. This is Travis Berger. So I said he did the whole Kepler input catalog. So this is this beautiful HR diagram that Dan showed yesterday. It's just pretty. So let's just look at it for a minute, because that's just pretty. I know I'm not even a star person, but you know, Gaia really revolutionized the Kepler data, and I love the Kepler data, so I'm a little biased. This is our beautiful HR diagram of the Kepler stars after Gaia DR2. It's gorgeous. Okay, and one thing that Travis was able to do with that new gorgeous HR diagram, now that he had better stellar parameters, he could better classify their ages using Dan's wonderful program that he just casually slipped in there with his list of isochrone fitting things yesterday. Dan's is the best. Use Dan's isoclassify. So he was able to better characterize the ages because he had better stellar parameters. And what he was able to see was that this planet radius valley looks different at different ages. So the green, if you're not colorblind, I'm sorry, the green is young planets, so stars that were found to be less than a gig-year old, yet less than 1 billion years old. And you can see that the peaks are at different places. So the super Earth peak is down here close to half of where the sub-Neptune peak is. Now for older stars with older planets, once you get older than 1 billion years old, that has evened out, that those peaks are now the same size. So what does that tell us about where did all of these super Earths come from at older stars? Why weren't they there for younger stars? Because they were sub-Neptunes and they've been getting shrunk down and now they're there. That's pretty exciting. This is actually telling us that these theories, these predictions are right, that they start big and they get pushed down small. That's really cool. It's also awful. It's super awful. Let me explain why it's awful. I showed you that we did not find any Earth-sized planets in the habitable zone with Kepler. But you may have heard that we have an estimate for how common Earth-sized planets in the habitable zone from Kepler are. Magic. No, extrapolation. We took the shorter period planets and we extrapolated out to longer periods because we're scientists and we were like, yes, let's do it. Let's just fill in this space. The problem is, let me explain the problem. The problem is if you extrapolate from shorter period planets, and that population of small planets at short periods is polluted by a stripped down population of larger planets, at longer periods, those larger planets stay large. They're not close enough to have their atmosphere stripped. The smaller planets down here get stripped. So you're like, wow, there's so many planets down here. There must be lots of planets out here. But you're wrong, because half of those, or some fraction, stayed up here. So you're going to extrapolate and predict a number out here, which is way too big. And so papers by, for instance, Ilaria Pascucci estimate that we've overestimated it by something like a factor of 8. That's not great. But it's something that we're trying to fix. And that's why it's a problem. It's exciting and it's physics and it's awful. So this is one of the ways that Gaia has helped us understand the Kepler results. Okay, so moving on to K2. K2 was that sequel to the Kepler mission. So on the left, I'm showing the HR diagram of the original epic, which was also Dan's awesome, amazing work. And none of this slide is a slight on Dan's amazing, awesome work. So the left is the HR diagram before Gaia DR2. The right is the HR diagram after Gaia DR2, which was a bunch of work done by a postdoc working with me, Kevin Hardegree-Ullman, to basically all of this purple down here. These are M giants getting erroneously classified as M dwarfs, and they're actually not, they're M giants. So with Gaia DR2, you're able to say, oh, that's not actually 50 parsecs away, it's 1,000 parsecs away, it's a giant. So you can put it in the right spot and you clean it up and it looks pretty. What we were able to do with that was to reproduce Kepler's planet radius valley in the K2 data. So remember, Kepler just looked at one patch of sky for 4 years and it found this planet radius valley, which was interesting. But it was just one data set, whereas K2 did that whole ecliptic. And what we did was find that the planet radius valley is ubiquitous. It's a feature of small planets. Doesn't matter where you look, in the galactic plane, out of the galactic plane, you see the planet radius valley. So we were able to confirm it in an independent data set because we were able to use Gaia DR2. And I have independent with an asterisk because it is the same telescope and a lot of the same pipeline hardware. So if you could construct some kind of odd bias in the Kepler pipeline such that it fit like a bimodal set of transit depths or something, and even that, like they tested 1 million times. I'm saying independent, but if you could convince me that there was a quirk, I would understand. But there's a planet radius valley in the K2 data as well. Okay, let's get to TESS. So you saw something very similar to this in Melissa's talk this morning. What was it? What are all of those? Clusters. Yes. This looks different. Does anyone know why? Yes. So this is ecliptic coordinates. I was really interested that Melissa showed the galactic coordinate version. I'm showing the ecliptic coordinate version. So I showed the ecliptic coordinate version because this is what TESS has observed. All of the tiny gray spots, basically just the gray shading, is what TESS observed in its first 2 years. So you can see it's almost the whole sky. And the point is TESS observed a lot of clusters. And Melissa did an excellent job of explaining why clusters are cool. So I won't go into too much detail. If you ever write a proposal, if you go into research and astronomy, you are required to use the word laboratory or you won't get funded. I'm sorry, it's just rules. So I'm explaining that now. It's good to know. Star clusters are astronomy's laboratory. The age, the chemistry, and the dynamical history are all controlled and correlated and well known. So Gaia has done 2 really cool things. One is help us with known clusters, help us constrain cluster members, help us constrain the stellar parameters, help us constrain the properties of those clusters in more detail. It's also, because of the incredible precision on the velocities and distances, helped us find new clusters, new groups of stars, new associated sets of stars, where you look at the dynamical data and you're like, oh yeah, that's all the same group of stars. That's cool. Now, star clusters, why are they cool? Oh, we'll get there. First, I want to say, this talk is about planets because it's a second summer workshop, but TESS and Gaia together are an incredible machine for so many other areas of astrophysics, especially stellar astrophysics and solar system science. So just as a side note, TESS and Gaia together are a match made in heaven for many fields of astronomy. Okay, I'm going to stop for a second. Snap poll. Which name of a new star cluster found by Gaia is worse? The Gaia Enceladus sausage. I think Melissa talked about this morning. Or Group X. All right, put your hand up if you think Gaia Enceladus sausage is the worst name. All right, that's a lot of people. Group X. Okay, so it looks about 60-40, sausage is worse versus Group X is worse. Side note, astronomers should not be allowed to name things ever. Okay. So why is it interesting to find new clusters and to do a better job of characterizing clusters with Gaia and TESS? We talked a little bit about planet formation theories, right? And why that predicts a planet radius valley. Planet formation theories also predict different time scales of planet formation. Some theories predict that planets form incredibly fast and they're there by the time the disk is gone within 1 million years. Some are, require that migration happen over hundreds of millions of years to end up where we see planets today. So understanding the time scale of planet formation is really key to understanding which are the dominant physical mechanisms that drive planet formation and evolution. So being able to have Gaia tell us which stars are in which clusters and be able to age date those clusters and have TESS be able to help us find planets in those clusters is really amazing. Because ideally what you want to do is map out the occurrence rate of planets as a function of time. You expect 0 at the dawn of the star because they haven't been built yet. But then how quickly it asymptotes to the field value. So Kepler stars are just boring middle-aged main sequence stars. So how the, I want to stay on the side of the tape, how the population transitions from 0 to the Kepler value is not known. When that transition happens, is it slow? Is it fast? Where does it happen? Different planet formation theories predict different shapes of that transition. So being able to map out planet occurrence rate as a function of age using these clusters is key to understanding these planet formation theories. Gaia gives us the positions and velocities of the cluster members. From TESS, we get rotation periods, which is a nice bonus as well for constraining the age from another direction. And TESS gives us planet candidates. So this is just an example. This paper by Sun et al. They looked at, I think, like 1,100 clusters. There's a lot of clusters, and found a bunch of planet candidates. And they're super valuable because they have this property of being in astronomy's laboratory. Okay. Young stars are hard, though. I will start by saying that. There's a reason why a lot of people just stick to the Kepler stars. Middle-aged stars are pretty chill. You know, it's your Gen X parents. They're at home listening to the same CDs they've been listening to for a long time. Yeah, it's still CDs. But young stars are doing a lot, right? They haven't had kids yet. They haven't settled down. There's a lot happening. So this is an example of a young star. This is a paper by Elizabeth Newton. And you can see this is 3 different data reductions of the same light curve. So it's one star, it's 1 sector's worth of test data. So that's time on the x-axis and flux on the y-axis. And there are 2 transits in this data. I'm going to just give you a second to see if you can find them. So this one's a little bit obvious. This one is tough. This one is tough. But this is why it's hard to actually do this in young stars. So for a long time, people just didn't, but Gaia has made it so much easier to find young stars that, you know, it's like thrown down the gauntlet. Go do it. Find planets around young stars, people. These are the transits. So far, when we've shown you, hey, this is how transiting planets work, it's been like beautiful light curves. This is what the data really look like. It's gross, especially around young stars. But this is a planet that Elizabeth found around a young star. And so what we've got now, well, I say now, as of a year ago, there were 30 planets that had been found between K2, which is in green, TESS, which is in yellow, and Kepler, which is in blue, in these young clusters. So 30 planets that have been found in young clusters. And someone in the audience, if he's still here, Luke found several more in Kepler, which I'm about to talk about. So this is at least a year out of date. But this is showing you the power of Kepler K2, TESS, and Gaia, that we can find these planets in young clusters and start to calculate the occurrence rate of planets as a function of age. Okay, 8 minutes, doing good. Okay, this is Luke's work that I just mentioned. So this is the Kepler field. This gray odd rectangular shape here is the Kepler field of view on the sky. The black spots here are the cluster members that Luke identified using Gaia data. And you have a bunch of Kepler candidates. And what Luke was able to do was to find that 3 already known Kepler candidates were actually members of this cluster, which is huge on the sky. So, you know, this is like more than a hand's width on the sky of these cluster members. That's like 60 degrees, so a huge chunk of sky. But they're all associated with each other in velocity space and in chemical abundance space. So he was able to add 3 more Kepler planets. And I just like this because it kind of shows why Gaia is important, because we knew the Kepler stars really well, but the cluster is much, much, much bigger than Kepler. And in a given patch of the sky, there's pretty low density of members of this cluster. But if you look at the whole, if you have Gaia, if you have everything, then you can step back and see this huge cluster and see which parts of Kepler, which candidates from Kepler are in this cluster. So I really like this figure because it shows the power of the 2 together. The other thing that's very cool, our galaxy ate a bunch of galaxies to get to where it is today. And the Gaia Enceladus sausage, as we just discussed, is actually one of those galaxies. It's the last major merger event of our galaxy. It ate another galaxy and just shredded it. And we can see those shreds left behind. We can see streams of stars from our galaxy eating other galaxies. But those other galaxies had planets, and now those planets are in our galaxy. So this has already happened before in the Kepler data, but now there's much more scope for identifying extragalactic planets, planets that were born in another galaxy with different dynamical history, different metallicity history, and are now in our galaxy. It's like time travel, space travel. We can actually see planets in other galaxies right here. So that's just a little side note, extragalactic planets. Okay, this is the last cluster I wanted to show, and just because this image again is so pretty. So this is another group. This is Melange 3. I didn't actually put this in the list of badly named clusters because melange actually means mix, and I'm on board. I'm okay. I have vetted that and I have decided it's okay. So this is an image. These are Kepler stars again, and what you can see are 2 arrows for 2 Kepler planets, the yellow arrow and the red arrow. And this is showing galactic latitude and longitude, the direction of the velocity. The transparency is how far away from the central planet it is. And the color is the velocity difference. And I just love this way of showing, like at night when you're driving into the rain, right? And all of the raindrops kind of feel like they're coming from one point towards you. That's what it feels like. You can understand on a more instinctive level why these stars are the members of the same cluster. They have such similar properties all surrounding this planet in the middle. All right. Okay. The last thing I'm going to talk about in terms of Gaia helping us understand things is stellar multiplicity. So this is a star with Kepler. Kepler had 4 arcsecond pixels. So each of these pixels is 4 arcseconds. You observe a transit on the central star and you say, hey, it's 1% deep. Cool, that could be a Jupiter. We can use the equation that Dan showed yesterday, which shows us the relationship between planet radius and stellar radius to get transit depth and go, cool, I know how to turn this into a planet radius. Except if you actually look really closely at that star and realize it's not 1 star, it's 3 stars, and that the transit is happening on one of those stars, the true transit is deeper because it's been diluted by the flux from the other stars. And the true planet radius actually needs to be corrected by the flux ratio between the flux from the star that the transit's actually on compared to the total flux in that pixel. So you will get your planet parameters wrong if you don't understand your stellar multiplicity. If you don't know how many stars are contributing to your light, you will derive the wrong planet parameters. That's a TESS pixel. So TESS pixels are 21 by 21 arcseconds. So there's even more stars in a given TESS pixel than there is in a Kepler pixel. How big a problem can this be? So this is showing for Kepler and K2 TESS. If you have 2 stars, one's a primary and one's a secondary, if you assume that the planet is on this primary, this is about how wrong you will get the radius, about 15%. If you assume that the planet is on the secondary, it'll be wrong by 50%. So your planet radius will be wrong by 50%. And similar numbers for K2 TESS. So this is just a typical dilution by crowding in the aperture. It's bad. All of that planet radius stuff would be totally washed out if you had 50% uncertainties on all your radii. So how does Gaia help us with this? Gaia helps us because, first off, Gaia just shows us all of the stars down to separations of about 0.7 arcseconds. So we already, the Kepler pixel 4 arcseconds by 4 arcseconds, we already now know where all the stars are at least, and we can do the dilution factor. But Gaia helps us even more than that. What if I told you there was one weird trick that astronomers love? Gaia measures the astrometric noise. So Gaia is measuring the position on the sky, and each of those positions has a noise, an uncertainty associated with it. And that uncertainty, if it was just a Gaussian distribution, would be symmetrically distributed here. It would go up and it would go down, and it doesn't. So the astrometric noise actually goes up, and then it has this really long tail to large uncertainties. So this is the renormalized unit weight error, and there will be a quiz at the end, but everyone just calls it the RUI. And it's a measure. Gaia gives you the RUI for every star, and it's a measure of the noise. If the RUI is 1, then your uncertainties are perfectly well behaved for a single star. If your uncertainty is big, if your RUI is bigger than about 1.4, then you're probably not a single star anymore. You're probably an unresolved higher order multiple, like a binary or a triple or quadruple. And this long tail of higher and higher uncertainties out here is because of all of these higher order multiple systems. So this is really neat. Every star now literally just has a number that gives you a really good idea straight off the bat whether it's a single star. And this was a quote from a paper by Carl Ziegler. The median RUI value for resolved close binaries is 5.56. So if you know there's 2 stars and you measure the RUI, it's 5. So that's like out here at 5. Compared to 1.04 for wider binaries. So if your binaries are so far apart that they're not actually affecting each other's uncertainties, then you get back to your uncertainty of 1 on each star, right? They're separated enough that they're not interfering with each other. The uncertainty on this one is 1, the uncertainty on this one is 1. And for single stars, it's just 1. So already you can see from this that if your RUI is about 1, you're probably a single star, or at least you're not so close to another star that's messing you up. And if your number is bigger than that, then you're not a single star anymore. Why is this useful? This is a K2 candidate and it has a Rui of 4.89. So until I saw the Rui, I was like, oh, well, it's a little V-shaped, but it's not dire. It's a pretty short period, but I mean, it could just be a short period grazing. It could be. And then I saw the Rui and I was like, no. It's an eclipsing binary. This is from, because I've given it credit for every plot. I had to put, this is my spreadsheet of retired candidates and lost streams. This is where all my candidates go to die when they have a Rui of greater than 1.4. Sometimes I get really optimistic and I'm like, 2's not bad. And then I go and I get higher resolution imaging and it's a double. And I'm like, should have listened to the Rui. Anyway, it's a really great trick. Gaia helps you take your list of hundreds and hundreds and hundreds of candidates and get that down. Okay. Gaia also, this is the depressing part. As if throwing away candidates wasn't super depressing. Gaia also helps us refute planets. So this is a radial velocity curve of HD 92987b. It had, when it was published, a minimum mass of 17 Jupiter masses. So it's pretty big, right? But the Exoplanet Archive goes up to 30 Jupiter masses, just in case. And then Gaia came along. So there's another mission called Hipparchus that was mentioned yesterday by Todd and others that happened, 20, 30 years ago. So even though we don't have full orbits for Gaia yet, you can combine the accelerations from Gaia with the accelerations from Hipparchus and get a Hipparchus Gaia astrometry, basically. So you can actually solve for the inclination. So that minimum mass of MP sin I, it turns out the inclination is 175 degrees, which is very close to 180 degrees, which is exactly pole on, which is the exact opposite of what you want. So it's not 17 Jupiter masses, it's 270 Jupiter masses. It's a star. So that one has to come out of the archive. And I'll finish by talking about the first planet. So I mentioned at the start of the talk that there was that plot of when we started finding planets. And you might have heard numbers like 1992 and 1995, but the plot showed 1989. And that was because HD 114762b was published in 1989. And it had a mass of 11 Jupiter masses. This was Dave Latham's planet. Now, they were like, it's likely, a brown dwarf or a substellar object because this is a minimum mass. So conservative, right? Literally every other radial velocity group since then has been like, 11 Jupiter masses, it's a planet. We've done it, folks. Put it in the archive. And these guys were like, well, it's a minimum mass, so maybe not. I have literally stood probably even in front of the Sagan workshop and mildly trash talked Dave Latham for not claiming this as the first planet. Guess what? It's not a planet. Oh my gosh. Turns out you can be conservative and right. 220 Jupiter masses. The Hipparchus Gaia came out and they showed it is actually nearly pole on. It is not a planet. Dave was right. I swallow my words. I was wrong. So now we have to take that out of the archive as well. And there's many more of these coming. All right. I'm into my question time. So I'm going to stop by saying that DR3 has a lot more data and we will answer a lot more of these interesting demographics questions. Read this slide at your leisure later. And then DR4 is going to be covered in a lot by Tim's talk and Alessandra's talk tomorrow. So there will be full orbits for everything, which will be super cool. And the exoplanet catalog is going to come out in DR4. There's 20,000 cold Jupiters are going to come out in DR4. That's going to be wild. That's going to revolutionize the field. Thank you very much.
Thank you, Jesse, for a fantastic talk. We have time for questions. Start, yeah, in the audience. There's no, sorry, we only have one mic.
And we expect you to go and stand at the empty stand.
There are plenty of closed binaries that would have Rui less than 1.4 as well. For example, hygroscopic binaries with equal mass would fail this test. So with that in mind, what would be the fraction of Kepler exoplanets you would think would actually be stars?
Oh, okay. So for Kepler, most of the planets are small with Kepler, so you have to, it has to be diluted by a lot to turn into a star. I don't have a good feel off the top of my head for what that fraction would be. It's a really interesting question. I think now we have a pretty good handle on the singularity of most of the stars. I would guess it's less than 10% that could really inflate all the way to being a star. But thank you.
How can you tell if a planet came from another galaxy? This is the first time I've heard of extragalactic planets, so it's pretty wild to me.
Yeah. So our galaxy formed from a merger of many smaller galaxies. So we just eat galaxies. There's a bunch of dwarf galaxies that are hanging around that will eventually get eaten. Those dwarf galaxies have planets in them that formed outside of our galaxy that are somewhere else. So as we eat those galaxies, the super interesting thing, so I'm married to a galaxy dynamicist, so I get to talk about this all the time. Galaxies are mostly empty space. So when two galaxies collide, it's not like anything hits anything else. It's almost all empty space. That's cool, right? Like, you hear about the Milky Way and Andromeda are going to collide. Nothing's going to collide. They're just going to go through each other, and the gravitational potential is going to slosh back and forth until they become a new thing. So when galaxies get swallowed up, the planets are fine. The planets are safe. They just stay next to their star. Almost all of them will be fine as compared to getting stripped. So all of those stars in that original galaxy that got swallowed up by the Milky Way still keep their planets largely, especially the close-in ones that we're most sensitive to. So this had already been done before Gaia. There was a Kepler star that was found that was in a known stream, which was an extragalactic stream. So at least once before Gaia this had happened, but it will happen a lot more with Gaia as we identify these streams from shredded galaxies.
Thanks.
No worries.
So there's a related question on Slack. So how many extragalactic planets are actually known? So
It's a very handful or less, like
not a whole lot.
a few.
But there will be more.
Yeah.
All right, let's take another one.
My question also has to do with the Rui parameter.
Yeah.
My current understanding is that it's essentially a measure of the residual after fitting for the various perturbations that we think are there. And if your Rui is significantly less than 1, is it correct that that could signify some overfitting? And is there any example of that happening in the Gaia data?
Oh, yeah, that is really interesting. I have not heard anything about small Rui values. I mean, I'm in the market for things that help me cull planet candidates. So I was interested in the higher end. But if there's someone else here who might be able to answer that.
We'll have Anthony come up and answer that.
Yeah.
Help answer.
Yeah, this confuses a lot of people, so it's a good question. But if you make a least square solution of a perfectly normal linear system of equations, and you look at the chi-square distribution, I'll take this off, it's easier to breathe, then you will in fact see that there are chi-square values well below 1. It's just because it's an actual distribution, but the peak is at 1. And that's why we always say, okay, if it's above 1, it's a bad fit, but you can have values below 1. So there's basically nothing wrong with the low Rui values. That's the main point. Yeah. And I was just wanted to, now that I'm standing here anyway, just one more way in which Gaia helps, in particular TESS, is that whenever there's a TESS candidate found, we actually check for them whether it's not a background eclipsing binary, and then we tell them, okay, don't waste your time on following this up.
Because you have photometry as well.
Yes, exactly. Yeah.
There's one more question on Slack that we can get to.
Oh, and Todd wants to ask a question or to make a comment. Go Slack first.
All right. So the question is about how do the properties of exoplanets depend on the type of the host star? If the star is old or young, or I guess it's generally about correlations between host star properties.
Yeah, so I would have to start the whole 45 minutes again to address that. Suffice to say that there are strong correlations between stellar types and planet parameters, and in the Slack I can put some references.
Right.
I'm inspired by Jesse.
You need
Everybody stand up. We have a new dance. It's called the Transit Mission Dance.
Well, we should add Gaia as well, though, because this is Gaia doing this.
We can get to that. So for transit missions specifically, we have Kepler, which stared at one spot. So everybody put your hand up. And then it kept twisting. So do that. So that's Kepler. And then we took that spacecraft and made it into K2. We went here and here and here and here and here and here. And if you do it right, you go the ecliptic, right? As you go around. And then, of course, we have TESS, which started in the south first. Drop the mask. Ready? We go scanning and scanning and scanning. But then we go scanning and scanning and scanning. And then you do it all again because they've done it at least twice and now they're starting the third round. And what was the last offering? Oh, Gaia. So Gaia does sweeps. Need more space. I'm getting out of the camera. Remember, Gaia does sweeps like this. So everybody do this. And now you have to do that for almost 11 years.
Thank you, Todd. Thank you, everyone.